Everyone, and thank you for joining in today. Welcome to today's topic, non-destructive nature of high voltage testing for motor insulation. Here in our webinar platform, you'll be able to learn more about our presentation, or you can move our presentation space around to your liking and learn more about our presenter team over here in our speaker bio, as well as being able to take our survey at any time or contacting us over there. My name is Michael Fleischer, and I'm the digital marketing analyst for Megger, and I'll be acting as the moderator for today's presentation. Sorry for the mind skip, and supporting you in any technical issues or questions for our presenter team. On the left side of your screen, you will see Ask a Question window right there. You can submit questions at any time during the presentation, and we'll go through those questions during the Q&A session at the end of the presentation. Additionally, your certificate of attendance, a copy of the presentation, and a link to the recording of the webinar will be sent to all attendees in 2 business days. Our presenter today is Swapnil Marathe, Applications Engineer. And to assist with our question and answer session, we also have joining us Scott Labruska, Baker Sales Manager, and Louise Beltran, Business Manager for Latin America and Canada. With that, I'll hand things over to our presenter. Thanks for joining in today, Swapnil. Appreciate it.
Thank you, Michael, and thank you everyone for joining in today. So we'll just go ahead and start with the presentation. Before that, I'll just turn off my camera so that we all have a good bandwidth and you can, there's no issues with the connection. Okay. Yeah, good afternoon, everyone, again, and thanks for joining again. So as we have the topic of today's presentation as non-destructive nature of high voltage testing for motor insulation. We'll go over the agenda of the presentation first, and we'll see what topics would be covering into the presentation. So first of all, we'll see the dielectric strength of the motor insulation. We'll go into see the dielectric strength of the slot liners, dielectric strength of the wires, and we'll see how strong the dielectric insulation is. Next, we'll move ahead to the hypot testing. On the insulation curve, we'll discuss on the insulation curve, how does hypot testing and surge testing helps us understand where our motor stands on the insulation curve. We'll discuss the DC hypot testing. We'll discuss the type of DC hypot testing. We'll later on discuss the surge testing, and then we have few case studies as well which justify today's presentation. So I'll just go ahead and start the presentation slides. So the dielectric strength of the slot liner. So on the screen you can see at 28,000 volt DC is a combined insulation to ground for a 460 volt motor. So for any pure electrically insulating material, the maximum electric field of that material can withstand and under specific condition, the electrical breakdown, or it can avoid becoming electrically conductive. So the total insulation between one single copper conductor of a 460 volt and core of a motor is total 28 kV DC or 28,000 volt DC. So that compromises of 2 parts. Out of those 28,000, 8,400 volt DC is the enamel coating on the wire, on the copper wire, and remaining 20,000 volt DC are the slot liner dielectric strength, which usually consists of a sandwich of materials like Nomex, Mylar, and Nomex, and sometimes Mylar can be replaced by Kapton. And this insulation materials have a pretty good higher dielectric strength. For example, Nomex can withstand electric stresses of up to 18 to 34 kV per mm. And next we'll move to the dielectric strength of an insulated wire. As we've seen in the previous case, one conductor, which is enamel coated, has a dielectric strength of 8,400 volt DC peak to peak, and the 6,000 volt AC is the RMS insulation capability. So that's for one conductor. So if 2 conductors are adjacent side to side with in the same coil, it gives us the total insulation resistance of 16,800 volt DC, which is a pretty good insulation resistance or insulation strength. We'll see how the insulation life curve operates, or how the insulation life curve is for every motor. So this is typically a graph. I'll just use a pointer here. This is the shape of the graph for every motor insulation, and on the x-axis you see time, on the y-axis you see the different types of voltage. So 30 kV or around 28,000 kV DC is the ground to wall insulation we've seen in the previous slides. The 8,000 is the turns to turn. 2,000 is the test voltage. The blue line is the test voltage, 2,000 volts, which we usually do our high power testing and surge testing on. And this is the operating voltages of the purple line indicates the operating voltage of that motor. So the spikes which you see it indicates the transients which the motor sees whenever it starts. So looking at the shape of the graph, we can tell us that the insulation reaches at a particular level and then it lunges quickly. So once it reaches the motor start voltage, which is usually around five times the per unit value of the terminal voltage or the rated voltage, we see more voltage arcing happening, and more often that ends into motor failure, which is the bus voltage or the operating voltage of that motor. And there are various causes for insulation degradation, like thermal, chemical compositions, and mechanical wear and tear. So how does this insulation, or how does the DC high power testing and surge testing helps us understand where our motor lies on the insulation life? You can see on the screen we have 4 different zones. There's a good zone, non-linear, test fail, and then the motor fail zone. What we are trying to avoid is going to this zone. So as motor operates, or motor is in working condition, it's in good zone, over a period of time, let's say a 460 volt motor, in the previous slides we've seen it's 28 kV to DC to ground. So being able to determine that motor has entered its final stage of life, or the red zone, it's a key to an effective electric motor reliability program. So without the predictive testing, the motor failure will come without foreknowledge if we just perform low voltage testing, which usually happens at this bus voltage level. So what we are trying to focus on is the yellow zone, the non-linear zone, and the test fail zone. So with predictive testing, we determine if our motor, or if our motor lies in this zone, or we try to determine if there is some incipient failure that would result to motor failure in future, which would of course save us a lot of unscheduled downtime. So just repeating it again. So to find the problems up here, we need to test on the yellow zones and the orange zone, which is the high voltage testing. And there are various insulation failures. We'll discuss the major ones, which the DC high power or the surge testing covers. So moving ahead, see the insulation failure modes in a motor. So the first one is turn-to-turn failure mode, which is a major failure mode. It comprises of at least 80% of the electrical stator failure. So 80% of those begin as a turn-to-turn fault, which then transform into the coil-to-coil, and then eventually face-to-face, and it goes into progression. So it's very important to determine if the motor is having a turn-to-turn fault. And the only test which we use to determine turn-to-turn fault is a surge testing, which we'll cover in the upcoming slides. See all the details about surge testing. And just moving ahead with the turns-to-turns failures. What's the reason why turns-to-turn failure is the major fault in the motor? So as it is the weakest insulation in motor, there are various reasons for turn-to-turn fault. So the major one is the wear and tear between the moving components. So the likely points to find a turn-to-turn fault is located where there's where there is a lot of motion, where there's a natural where there are more natural consequences of the motion, and along with that, motor also is faced to different thermal and magnetic stresses. So the magnetic stresses on the windings can pull, which goes in opposite direction, can have a push-pull effect on the windings, which can degrade the insulation on that winding. So turn to turn, this and also the VFDs and the motor starts cause voltage spikes on motors, which also results into a turn-to-turn fault. So comprising of all these factors, we can determine, or we can come to a point that why is it turn-to-turn as one of the major failures. We'll see an auto transformer action of a welded form. We'll see how does it relates to our or today's topic of presentation. So when you get a shorted turn, so the localized current has another low resistance path to flow, and so it's a burnt fault, it's a burnt turn, and we all know that heat follows current. So, and heat is a squared factor of current. So the heat generated at that spot would be a squared factor of that the amount of current flowing through that on that fault. So for example, let's say a 16 turns, we get there's a 16 turn and we get a burnt fault or burnt turn to turn fault. The normal current would be 16 times more, and the heat would be the square factor of 16, which is 256 times more, which is a lot for the motor to handle. And according to IEEE, the welded fault turns would burn through slot liner to ground within 15 minutes. So that's pretty quick once it experiences the welded fault. We'll see a picture. As you can see, what probably would have started as a turn-to-turn fault and eventually ended up as a slot liner to ground fault, which represents the burning effect on that coil. So moving ahead, we'll see why early turns have major faults and also the insulation failure at the startup. So we all know voltage spikes, or what we call as current spikes, are generated at the start of whenever a motor starts. So the reason behind is this: we use contactors, we use VFDs to operate the motors. So whenever we use, for example, let's say we are using a contactor to start a motor. So these contactors are mechanical device. Of course, when they are switched on, there's a bounce on the contactor terminals of switch or the relays. So this bounce creates a magnetic field, and then the magnetic field collapses, which creates voltage spikes. So the right time of this spikes is around 0.2 to 0.5 microseconds, very short period of time. But this spikes can go up to 5 times the per unit value of that motor. So in this case, let's consider a 460 volt. So the per unit value we use to represent to have every parameters on the same page. So 5 times the per unit value, we get around 1960 volt, which is a lot for a 460 volt. But this is the voltage which a motor experiences every time it is started. And coming back to early turns fault, so majority of the turns failures start at the early turns, because these are the turns which face most of the voltage gradient or face most of the voltage spikes because of the position of that turns. We'll see how the voltage is distributed across the motor coils. So there are various different factors for voltage spikes. One of them could be lightning, which is around 1.2 microseconds, falls under this graph nearby here. VFD switching is around 0.5 microseconds, which falls around somewhere near here. So as per an IEEE standard, which calls about for 0.2 microsecond rise, the test equipment which we are using to test the motor should be able to gear up with all this 0.2 microsecond rise. And we have previously discussed, more voltage stress appears at the first turns. That's why motor fails at early turns most of the times. And there are various voltage spikes. There are various voltage spikes generated because of various reasons. We'll see how high this voltage spikes can go up to at the initial start of the motor. So as you can see, for a 480 volt motor, it can go up to 5 times the per unit value, which is around 1960. So, but if we look around a 13.8 kV motor, goes up to the 5 times of that terminal or per unit value is 56 kV, which is very high voltage. But this is the voltage which motor experiences, as previously mentioned, during transients or voltage spikes. That's why we do different types of high-pot testing and surge testing to analyze where does the motor stand on our insulation curve. We start with the DC high-pot test. So conventionally, a DC high-pot test is which ramps quickly to the target voltage and holds on for a minute or less than a minute and then measures the current. It's a very useful test to evaluate the ground wall insulation, and also it determines if it is approaching the end of life criteria, which is again going back to on the insulation curve. And it is also known as the ground wall stress test, because there are two types of DC high-pot testing which we offer and which we can do on a motor test. First of them is the step voltage evaluation. As the name suggests, the voltage gradient or the test voltage is risen on stepwise, and then the leakage current is calculated or measured to see the insulation of that particular motor. Another one is the conventional voltage high-pot test, which we discussed, as it ramps to a target voltage and holds for a minute. So in both tests, we are just trying to see the linearity of the measured leakage current. And then we determine the health of the insulation as according to how linear the chart is once we get the test results. And there are various standards to determine what our test voltage should be doing a DC high-pot. So as per what IEEE 95 suggests, our DC test voltage should be 1.7 times the AC test voltage, and it can be between 125% or 150% of a terminal voltage. So for a 4160 volt AC motor, our test voltage could be between 8800 volt DC or 10,600 volt DC. And there are common industry high-pot test voltages also suggest we just multiply the line voltage by twice and add 1000 to it to get our test voltage. So this was IEEE 95. We have another standard from NEMA. It also suggests that our DC test voltage should be 1.7 times the AC test voltage. After if it is already in service, we just add a factor of 0.75, or that is 75% of that calculated test voltage. Here we have an example of a 460 volt motor. So for a new 460 volt motor, we'll use 3024 volt DC, while in service we'll use 2448 volt DC. And again, the same common industry high-pot test voltage, just multiplying the terminal voltage by factor of 2 and adding 1000 to it. Let's see how a DC high-pot works. So we all know we ramp up the voltage, and then we measure the leakage current at the voltage higher than the in the terminal voltage or the rated voltage of the motor. So once the voltage is applied, there are multiple currents which start to flow on the insulation, and the DC voltage is applied to open windings by the high pot tester or the motor analyzer. So the DC voltage potential in the windings is rapidly raised to the predetermined level or raised in steps in case of step DC voltage test. So as this voltage is raised, there are several currents which flow and into and possibly out of the windings to the ground. And the combined or the total of all these currents is what the motor tester or the high pot tester calculates to give us the linearity or to give us the leakage current graph. So the first one is the capacitance current, which is also called the inrush current because the capacitive nature of the windings. So this current typically drops to zero within seconds. Next one is the absorption current, and this is usually present when we are doing a mega ohm test or a mega test at the rated voltage of that motor. So this current will drop zero after some time. And the third one is the conduction or the leakage current. So this is often referred to as a surface leakage current, and the surface conduction current runs over the end winding surfaces of that insulation. So combining all this current, we calculate and the high pot tester measure this current, which is the total current to give us to determine if the linearity of that DC high pot result. So we'll see what DC high pot test can help us find. First of all, the weak ground weak ground wall insulation, the cable insulation weakness, and of course the contamination level and the surface leakages. Face-to-face insulation, the dielectric strength on that face-to-face insulation can also help us find or delamination or voids. So if an IR or a mega ohm test fails, which is usually done at a rated voltage of that motor, we can conduct a DC high pot test to dig out more or on what part is the motor failing or what insulation is the motor failing on. So here I have a pop-up message from the software or the tester that the test failed on the mini mega ohm test. So we just conduct a DC high pot test to see if what's the reason. And again, we found an overcurrent was stripped. So definitely tells us there is some bad insulation on that particular phase. So we'll discuss something more on the DC high pot as per IEEE 95 standard. So it's usually as far as the IEEE 95 standard is considered, it's used the DC high pot. It's used or DC high pot testing is done on machines of 2,300 volt and above. But these methods have been really helpful in finding faults on low voltage motors as well. So it's just it's just the voltage changes whenever the rating of the voltage or the motor changes. Also, whenever the test is done, it's very necessary to discharge the energy. So the high pot tester and does that. It discharges all the energy. Once the test is done, it discharges the energy through the ground. We'll start with the step voltage test. See more into step voltage test, and of course after step voltage test, we'll see the ramp voltage test. So as we discussed, it raises the voltage in steps and then it holds the voltage for a minute, then calculates the current, the leakage current, and then it goes to the next step, then holds for a minute, calculates the current, same process does it for 5 times. So we will look, once the test is done, we look at the linearity of that measured current, on measured current can be which could be linear or non-linear depending on the points where the current is calculated. So the fundamental aspect is, whenever we increase the voltage or whenever we increase the test voltage, the current should remain constant, or it should increase with respect to that voltage, because the resistance is considered to be purely if the resistance is considered to be good, then that fundamental aspect appears to be true. So voltage increases, the current should increase as well. And like previously mentioned, any deviation could signify a defective insulation. And so at lower voltages, when we do the mega ohm test or the mega test, we might not be able to ionize that particles, or ionize the cavities or small gaps in the insulation, or the small wear and tear in the insulation, which can give us a false indication of the motor insulation. That's one another reason why DC hypot is tested. DC hypot test is tested, or the test voltage is higher than the rated voltage of that motor. Also, like discussed, as we discussed previously, it increments in 5 equal steps, and then stays there for a minute on each step, and then calculate the total leakage current on it. So and step voltage are used to detect physical damages like pinholes and or brittle insulation in aged equipment as well, because we increase the voltage more than the rated voltage, and then as there is insulation wear and tear, it could if the insulation is really bad, it could instigate an arc. But also if the insulation has a little wear and tear, we would see that on the graph. It of course helps us to determine or give us a predictive, or give us an incipient understanding of the motor insulation, and we can do some actions on that motor before it gets into a failure zone. So it's just an early warning of an incipient problem, which we would be getting, or we would be understanding from the results of the DC hypot test on the step voltage side. There are various standards. On the first one is the IEEE 95. The latest version was 2002. So this standard helps us to calculate the test voltage with keeping the rated voltage of the motor as a reference. So, for example, for a 480 volt motor, we would the minimum test voltage would use is 1020, and that was calculated by a factor of 1.7. And again, the maximum is 1224. So 125% to 150%, we can use any voltages, test voltages between this range and this range for a 480. Similarly goes on for various types of different ratings of a motor. And then there is also an ESA DC hypot standard, so which has a different, which is of course a different standard, which tells us if the motor is less than 0.5 HP or less than 250 volts, we use 1700 volts to do a DC hypot test on that motor. If it is more than that, we use the same 1700 volts and add it to 3.5 times the rated voltage of that machine. So there's both standards are useful to determine what test voltage should we use on doing DC hypot test. We'll see a case study here on two motors, how we can determine the health of an insulation, determine the health of an insulation according to the linearity, or after studying the linearity of the graph. So during the step voltage, you can evaluate the recorded step leakage current levels for linearity. by comparing the leak by comparing the change in leakage current between each step. So here you see, and this is motor 1, we'll see the leakage current calculated in first step is and the difference between first and second, or the further next step is zero point 0.5 microamps, which is constant. There could be some change here of around 0.40 microamps, which is still at under the standard. And this is how the graph would look. As the step voltage rises, it measures the leakage current. Next step holds there for a minute, moves to the next step, and then we get a graph of the leakage current. And as it's clear to our naked eyes, it's a quite linear graph, which shows that the motor insulation is still in good condition. While on the other hand, in this case, if you see, the graph is quite linear at this point, but as the testing goes ahead, as the voltage increases, you see non-linearity here. So you see once we see the test results, we can calculate the differences on the leakage current, calculated leakage current, and then determine the non-linearity from the graph as well, which helps us understand that the insulation is not so good on the motor 2, or and this was a case study done. So what was found as that the motor 2 had a high amount of internal contamination, which was caused due to accumulation of dust and oil. So here it was the chemical and the chemical composition and the mechanical wear and tear. So obviously, once you find there is an issue in the motor, we have some maintenance we have some maintenance program. It has to be done to repair the motor, or get it to a motor repair shop to replace the windings. Other one, so that was all about step DC hypot test. We'll see the other type of hypot test, which is continuous ramp test. So here, the ramp voltage, as you can see, there's no steps involved. It just shoots up to the test voltage and then holds there for a minute. The blue line indicates the voltage and the red line indicates the measured leakage current, total measured leakage current. The increase so you see the increase in the current initially is because of due to the capacitive current, and as soon as the test progresses, you will see if the insulation is not good, we'll see as increase in the test current or the changes in the graph. So capacitive inrush current rapidly drops to 0, which we've seen from the total currents, and the remaining current is measured. What is measured is mainly due to the surface currents and the conduction leakage currents. So the slope of the curve should be fixed for a good motor. That is, the curve should be a straight line. Since the higher voltage typically produces proportionally higher measured current. So again, we are looking at the linearity in the same test. Both the tests, we are looking at the linearity of the graph of the leakage current. So that's what was about the hypot testing. So the question arises now: so should we do a hypot testing on our motors? And hypot testing is done from like, it's a conventional test. There are various standards to determine why the test is non-destructive. So this is one of the article from the IEEE standards for rotating machine insulation 2001. So it clearly states that if a machine or if a motor has failed hypot testing, it is because it has some insulation degradation in the happening inside the motor. That's the only reason why a motor would fail and hypot testing. Because looking back at the standards, what we see, the test voltages which we see are comparatively less than what the motor experiences during the initial starts or the voltage spikes or the VFD switchings. So another good article or a good comparison is from the book of of machine hypot testing in electric utilities. And this is a good comparison which can sum it up why DC hypot test is not a destructive uh, test on voltage, and why it is very important. So they've just taken an example of a motor. If it runs for a 400 hour and is on and represent 25 years of service, so 1 minute of 29 kilovolt over a potential test at 100 degrees Celsius would take down the insulation by 9 hours. While if we do a DC hypot test, it can only at 30 degrees Celsius, it can only do about like 1/16th of an hour, which is like quite 3 or 4 minutes comparatively to the 9 hours, which the motor experiences every time in regular operations. So that was on the hypot testing. We'll move ahead with our next testing, which is the surge testing. So coming back to turn fault, or which compromises the majority of fault, as we discussed, that surge testing is the only testing which can help us find turn fault, and those are the major faults. And it's one of the tests which effectively uses the electrical resonance concept. We'll see in the upcoming slides how that concept is being used. And just to start with the test, the surge testing, just to give a background on that, what we are trying to see, and let's take an example of this surge waveform. What we are trying to see is all the three waveforms should superimpose on each other. So there should be a difference less than 10% threshold on all three, comparing all three waveforms. So here, it's definitely not the case what we see on the screen. The lead 3 or the yellow line is clearly out of sync with all the rest of the two waveforms, which gives an indication about turn fault or other faults as well. Paschen's law will, before heading to surge testing and to details of it, we'll understand what is Paschen's law. It's a good reference point for us to understand why this test, what we are conducting about the rated voltage, is not destructive. Also understand more on the surge testing as well. So this law explains why high voltage test can find to determine the condition of that motor. So you see, as on the graph, it requires a minimum of 325 volt to instigate an arc, and that is when the two conductors are displaced or at a distance of 3/10,000 of an inch, which is a very small gap. So even if there are bare copper wires, or there are bare copper turns, it would still need a minimum of 325 volt to instigate an arc. And again, one of the reasons why mega ohm or the mega test or the low voltage testing cannot find the issue what the DC because of the DC voltage distribution. And also this law has a good reference on that point, why DC hypot testing and why surge testing is necessary. And of course, the standards which we see help us to understand why those tests are not destructive. So moving ahead with, we'll see the principles on surge testing. What are the principles? So I'll just read this loud. So when a rapidly increasing current is applied to a coil, a voltage gets generated across the coil by the principle of induction, and that voltage of that coil is given by V is equal to L into di by dt. So V stands for the terminal voltage, L stands for the coil inductance, and di by dt stands for the change in current with respect to time. So the terminal voltage V at the leads of that coil is actually the sum of the induced voltage created between individual loops in that coil. So if the insulation that separates the coil is weak, and the induced voltage is higher than the dielectric strength of that weak insulation, an arc will form between those coils. So ultimately, what surge test does is it creates an induced voltage between an adjacent coils or adjacent turns, and it detects the arcing, which is an indicative of a weak or a failing insulation. So surge testing tries to replicate the real life phenomena or the real life scenario while doing the test. And here's a block diagram of what we use or what's the circuitry goes into surge testing. So first of all, there's a high voltage power supply. There's a high voltage switch. The motor is represented as an coil or as an inductor. So once the capacitor is charged in the high voltage power supply side, the switch sends in pulses to the motor, and there's a frequency call which is also called as ringing frequency, which the software analyzes through its algorithm after measuring the pulses and the rise of the pulses, or one pulse to the next pulse, and the pulse next to it. So the ringing frequency of that waveform is given by this formula. The R square by 4L square factor is very low, so we can eradicate that factor and just simplify the equation as 1 by 2 pi and under root of 1 by LC. So if the turn-to-turn insulation fails with an arcing short between two turns of the coil, a fraction of the inductance will be shorted out of the circuit. So as the inductance is shorted out of the circuit, the frequency will increase because this is inversely proportional. So the frequency will increase and the as the inductance decreases. So as the frequency increases, it will jump to the left of that ringing pattern. And of course, we'll see once we move it to the next slides what jumping to the left on the frequency or the ringing pattern means. So just to reiterate, if it is a sudden increase in frequency, that is an indication of arcing or turn-to-turn fault. And it also depends on the coil and the location of the arcing short. So the magnitude of the surge waveform may also slightly decrease, as we have seen previously, that most of the turn-to-turn faults occur at the early turns. So here is just a representation of the resonance circuit. We have the tester which acts as a capacitor. We have a motor which acts as an inductor. And so the internal capacitor is charged to a known voltage. So at a specific time, a high voltage switch, which we seen in the previous diagram, closes and transfers the charge from the capacitor to the windings of the coil. So if the resistance and the loss of the entire circuit as such that it is under damped, so the charge will be able to flow from the inductor to on the other side of the capacitor, which would result into oscillation, and that would be detected by the software algorithm and be displayed by the software algorithm as well. So the process of ringing will repeat, the ringing frequency will repeat until and unless the resistance and the losses in the circuit are completely absorb the energy that was displaced by this capacitor. And the measurement is of course taken on the terminal of the motor, or the terminal voltage conductors of the motor, and it is with respect to time, which gives us the surge waveform. And we'll see further ahead that those waveforms are damped oscillations. Excuse me. And we'll see the voltage drop over the turns in the next slide, which also helps us understand why the rise time is also important, or the rise time of that voltage spike or the test is also important while doing a surge test. So we create impulse of voltage in the windings and the voltage decays, right? As we can see on the graph, there's a high voltage at the initial and then eventually decays. So the non-linearity of the voltage drop, as shown in the figure, so appears during the spike of the VFD switching, or like the VFD switching or the contact is bouncing. So those and the first few turns experience the majority of that voltage. So that's why, as mentioned previously, search test replicates those real lifetime problems or those real situations while doing the testing. And when we apply higher voltage with the rise time differences, we can expose these weaknesses as we get the graph of the results, and we can determine the insulation condition depending on the waveform shifting to the left. And let's talk more details about the why the rise time is of an important factor for doing search testing. So this is an article from IEEE 522, which states why different voltages levels or test voltage should be used at different rise times. So the turn-to-turn voltage distribution of a search pulse is not linear. So it's across the whole winding. It's not linear. So, and we have seen in the previous slide that the fast rise time pulse will induce higher turn-to-turn voltage at the tested end of the coil than the ground end of the coil. So a higher turn-to-turn voltage at the tested end of the coil is observed and replicated by sending surge impulses as the pulse moves through the winding. Due to this phenomena, due to uneven distribution of that voltage, so IEEE 52 recommends that so different test voltage for different rise time pulses. So here we have the exact standards. So for 0 to 100 nanoseconds, we use the recommended test voltage is 1 times or just the per unit value of that motor. For pulse rise times between 100 nanoseconds to 1.2 microseconds, its test voltage, the recommended test voltage is 3.5 per unit, the rated terminal voltage. And if it is longer, if it is of more than 1.2 microseconds, we use five times the per unit terminal, 5 times the terminal rated voltage of the motor as a test voltage. And the high voltage switching networks in the in Megar-Baker search testers fall under 100 nanoseconds to 1.2 microseconds, and the actual rise time of Megar-Baker motor test equipments are closer to 100 nanoseconds, which comply the standards of IEEE 522. And here is just a graphical representation of the rise times and the different rise times and the different voltage levels what we use for different rise times. So there are different standards which we've previously seen for DC high-pot. There are different standards for test voltages. There are different standards for surge test voltages as well. So we'll see a combined combined test voltages for both high-pot and surge. So there are various standards like previously mentioned, IEEE 95, there's ESA DC high-pot, and there's IEEE 522. IEC is a European standard, which also which is more, of course, more used in Europe. And then there's Baker standard, or we can say just to calculate the test voltage with reference to the rated terminal voltage of that motor. We can use just simple, straightforward. You multiply the rated test voltage by twice and add 1000 to it. So different types of motor rating voltage, and then again, as per the standards, various standards. If it's in service, if it's a new motor, if it's in service and new motor, what test voltage should we be using to do high-pot and surge testing? So let's discuss more on the algorithm which we use to calculate the differences between the waveforms which we discuss in the search testing. So it's called error area ratio, which is EAR, and EAR plus is an updated Baker pattern. So it's it's an algorithm which calculates the difference between the two areas. Let's say we have one waveform, then we have another waveform, and then the difference between the difference of the areas on those two waveforms are calculated by algorithm. So we are looking at this threshold. So as mentioned previously, it should not cross over 10% of the threshold. This is the area which we are looking for, and if there's a third curve, it would be comparing all three curves. So this area should not, or the threshold should not cross 10%. If it does, the software would recognize that, and it would give us a failed test indication. So also on search testing, there are two types of search testing which we can call. One is the pulse to pulse EAR, and other one is line to line EAR. And the algorithm, the concept, or the methodology is same. There's just a difference of few factors, and we'll see the pulse to pulse EAR test first. So pulse to pulse EAR is of course it uses an EAR plus algorithm on the subsequent pulses, the pulse which was sent next, and then the pulse after that, just to observe the change in the shape of the waveform as we increase the test voltage. So when we allow, when we start at the low, or when we do a search testing at different voltage level and we ramp the voltage, the software does analysis of each ramp level. So it determines the area under the curve, and then that gets compared to the next pulse, and this is done all under one phase, and the graph is plotted out for all those pulse differences. So waves from excuse me, waves from each search pulse are compared as the voltage increases. So usually for windings with non-symmetrical electromagnetic fields or single windings, we use the PPEAR test, and usually used in motor repair environment. So there's no difference in the graph in the waveform, and the whole point of doing the PPR test is to avoid the rotor influence, which can give us a false test results. Like I said, it was usually used in motor repair environment, just to see if all the waveforms are superimposing or in sync with each other. We'll see few examples on the pulse to pulse EAR. So here are two examples which clearly failed the pulse to pulse EAR. So two exactly identical waveforms will have an EAR of 0.0%. So there would be no difference on those two waveforms. If the two waveforms that look identical to the eye or to our eyes, that can have a difference of 4 to 5%, but that's still under the standard or accepted values. And we would notice a change, or we would notice the unidentical waveforms if it is more than 10% or higher. So here in the first test which we did, as you can see, the blue and the red lead are mostly in sync with or in phase with each other as the number I am large. So lead 1 is 1.7% and lead 2 is 1.8%, while lead 3 crosses the threshold of 10%, and then the software will let the equipment user know that the test has been failed, and we can do more digging into lead 3. Similarly here, as we see, lead one was lead one was tested and used as a reference waveform, while while the test was running on lead two, the tester or the motor analyzer found some faults, or that's where the ringing frequency changes, and then that's when the waveform moves to the left of the standard or the reference waveform. And of course, if the difference is more than 10%, it would give us a failed result, or and then we can look more into the insulation of that motor. So this was about the pulse to pulse EAR. Look what is line to line EAR. So line to line EAR, or line to line error area ratio, is it's a way to quantitatively determine the difference of the waveforms from two phases of a motor. So the thought here is the surge waveforms for all three phases of a motor should be nearly identical. So if the waveforms are not, there should be a hard or bolted short in one of those phases. That's what line-to-line EAR would help us determine. So so the line-to-line works well with motor without the rotor installed, because the coils are nearly identical, and testing assembled motors or rotor installed is not straightforward. It's not straightforward because depending where the rotor slots are with respect to stator coils, there would be a different coupling ratios for all three phases. So usually it is recommended during field testing, we do not compare the waveforms used pulse to pulse EAR, and for motor shop testing, where we have to compare the waveforms, of course, when there is no rotor influence, line to line, we can use line to line EAR. We'll see a case study of a surge testing. So let's move ahead and see the case study of a surge test which we conducted. So as you can see on the screen, lead one, the peak voltage or the motor failed at first lead around 4,000 volts. The target test voltage was around 9,700 or 9,000, around 8,000 volts. So lead one clearly failed the test. You can see the pulse to pulse jumping and crossing the threshold. And again, as the inductance changes, the ringing frequency changes, and then the waveforms of that particular lead moves to the left. So as red or lead one failed, you can see the moving of the waveform to more to the left side, while the green and the blue are under the limits and almost they are in sync with each other. So even in this, when this motor was tested, all the other tests which we do on the motor, the low resistance testing, the resistance testing, or the low voltage mega ohm testing, the PI polarized index and the DA, all tests were passed. But it's another good case study to help us come to the point why surge testing and DC hypo testing are as important, or much gives you much more results on the predictive side of the maintenance program. So so of course the motor was sent back, checked on, and it was up. So this was a case which was done few years back, and the company saved a good amount of money on the unscheduled downtime. So they were able to determine that the insulation failure or the insulation level of that motor before the motor went to the failure zone. And of course it saves everybody, or it saves the company, a good amount of money, and most of all unscheduled downtime. So we'll see the maintenance program and what are the types and benefits of the maintenance program. There are three types of maintenance programs. It's a reactive, which is run to failure. We let the motor run until there's a failure detected on that motor. So preventive maintenance program is conditioning or checking the motor sleep at a particular intervals during the year, even if the motor is running at a good condition or it's running regular operations. And predictive testing is what we are looking at, which gives us the maximum ROI. It's almost 10 times what reactive could give on, and almost twice what preventive maintenance program could give. So, and also predictive maintenance, it decreases total maintenance by 25%, while preventive does it by 19%. And reactive, of course, we let the motor run until it fails. So the whole point of surge testing and DC high power testing or doing high power testing, of course, these tests are conducted not at a voltage higher than the rated voltage, but as we've seen, the different standards or different real scenarios where motor has to run every day in operation, faces more higher voltage, more higher spikes than what our test voltage is for that rated voltage motor. So just to summarize all of the presentation, excuse me. Just to summarize all of the presentation, see, of course, we have the standards which determine the DC high power is of course a non-destructive test on motor, and it's very important. Also, surge, the energy which we use in surge testing, the energy is low, so the arc energy is low, and for a 460 volt motor, even the arcing happens around like 10 kV, and for 460 volt motor, the surge test is conducted around like 2000 volts. So whether we are aware of it or not, we high power and surge test our motor more frequently than we realize in regular day-to-day operations. And each motor's start and stop effectively are effectively a high power test and a surge test with unlimited amount of energy, which can damage the winding. So using a static tester, doing a surge test or doing a high power test means we are simulating the same scenario but with low energy and precise control manner, which does not harm the insulation of that motor. So with low voltage testing or insulation testing, it has an important part to play, but it's not wholly adequate for us to evaluate or give us a bigger picture where our motor stands on the insulation part. So with all these facts and with all the standards and with all the case studies, I think it's we can come to a conclusion that the high power testing and surge testing are definitely not destructive, and as they also play a major part in understanding where our motor stands on the insulation curve, saving us a lot of downtime and saving the company a lot of on downtime and money. And I think this was the last slide of my presentation, and I'll just take this opportunity to let everyone know that Megger Baker has launched a new static tester. It's called ADX, with very nice upgraded features. It has a PowerDB dashboard with cloud-based analysis software. It also has asset management tools. It can keep record of how many motors you have, what are the test results on those different motors, and also it is designed to perform test voltage up to 15 kV. So I have mentioned the YouTube link for the video for the unit, the new launch unit, and also the other link if you want to get more details. You'll see more details on the unit, more data specs on the unit. So again, my name is Swapnil Marathe. I work as an application engineer at Megger Dallas. So I think, Michael, we are ready for questions.
Yeah, it looks like we did wrap up our presentation portion of our webinar. And a lot of you who are frantically jotting down those URLs to view this video or the more information for the ADX, we'll be sending those out in our email after our webinar. If you'd like to learn more about the ADX, we actually have a link there in the related content as well. But as we jump into our Q&A session, I'm going to give a little bit of housekeeping points as our presentation team gets their cameras and mics turned back on for our Q&A segment. For those of you that are leaving, we will have a survey pop up. We would really appreciate it if you take a couple of minutes to let us know how we did today and how we can improve upon our future webinars. As a reminder, a copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be sent to all attendees in 2 business days. You can also view video recordings of previous webinars as well as register for upcoming webinars on our website at us.megger.com/webinars and register for our next webinar on July 22nd, Innovations in Power Factor Testing, presented by Ken Petroff over there as well, in addition to our What's Up Next button right over there. So with that, we're going to jump into our Q&A session. It looks like the first one I have, I'm going to be directing over to our panelist, Luis Beltran. Luis, if you find your microphone and camera button, I'll send this over to you. Hey there, Luis. So This question is, for weak insulation, shorts, or open coils, can I get those problems in the inductance test?
That is a good question. So if we have a short or open coil, so we got a problem. So the problem is there. I mean, we don't have to do or to work in the way of to predict something. So if you are doing the inductance test, that test is made in low voltage mode. So I think you can identify opens or shorts, but the weak insulation, that is impossible to detect using the inductance test. So the only way to work in a predictive way is to do the surge test in order to identify the weak insulation. That is the only test that you can do. Okay, thanks.
All right. Thanks, Luis. Oh, nice, Scott. Popping up. Speaking of, this next question's for you, but before we do, I will remind everyone, if you have any questions, please feel free to submit them in the Ask a Question box, and we'll get to them here in our Q&A session. So, Scott, does your test equipment do DC or AC high pot tests? What is the difference?
Thank you for that. So for predictive maintenance and for typical motor repair, probably well over 99.9% of the tests, as far as between the AC or DC high pot, it's the DC high pot. AC high pot is used almost exclusively in motor manufacturing, not totally exclusively, but mostly in motor manufacturing. It's a underwriter's laboratory recognized test. It's usually a requirement for production line OEM motors. And so they will do the test there. The big difference between the tests are, well, one of them, of course, the nature of the actual voltage being AC or DC, but also the current that's used. So in an AC high pot, there's milliamps of current. And in the case of DC high pot, it's usually, just microamps. So here's the difference. If you have a motor that's running in industry and you find, say it has some insulation to ground that is compromised, you can find that with the DC high pot with very, low current, and it's current limited, so it doesn't get runaway current and, damage your winding at all. Where an AC high pot, if you had that same problem, the amount of current that's used in an AC high pot will burn and destroy the insulation, but there has to already be a problem there. So that's why AC high pod is not used in predictive maintenance typically or motor repair.
Thanks, Scott. Our next question I'm going to throw over to Louise. What is the difference between the pulse-to-pulse and line-to-line error?
Okay, so the pulse-to-pulse error is made during for each individual waveform. I mean, when we are testing a three-phases motor, so we are going to test the line 1, so we are increasing the voltage, and we will have a waveform increasing. So the error is called pulse-to-pulse. So we are trying to identify weak insulation when we have a movement of the waveform to the left. And that error is going to calculate the percentage of the differences of waveforms. The line-to-line error is when you have completed the 3 lines, I mean the search test with the 3 lines, so you will have 3 waveforms. So you are going to compare 1 to 2, 2 against 3, and 3 against 1. And in that way, you can identify shorts or opens. That is the difference. Okay, thanks.
Thanks, Louise. While I have you, this next question is also going to go to you. During the surge test, we have the value of the ear equaling error area ratio. Is this part of any IEEE standard?
Okay, I think this is related to the EAR, error area ratio. So this is not part of the IEEE. Actually, this is a Baker invention. Now we are Megger Baker. So Baker invented, and we filed the patent of this invention in 1989. After, I don't remember, some years after we filed the patent, so the patent was open. And there are other companies that they were trying to copy our patent, but that is impossible because the algorithm and the software that is written in and put it inside the equipment, so nobody can copy that patent. Actually, we updated or we improved that patent with our new ADX tester. So now we call EAR plus trademark. So now our tester is more sensitive in order to identify weak insulation at the very beginning of the problem. Thanks.
Thanks, Louise. Now I have a question that I'm going to pose to the 3 of you, just as we don't have one assigned yet. In Megger's experience, will a turn-to-turn fault always show itself during testing with a resistance imbalance?
I'll take a go at that.
Okay.
So a turn-to-turn fault, it first of all, needs to be clearly defined. There's as Swapnil had mentioned, there's turn-to-turn weakness, right? So there's your copper windings that has, each strand of copper, or in the case of larger motors where you have copper bar that's wrapped with glass tape, typically. So there's a huge difference between insulation weakness between windings and an insulation, we'll say, short. So the surge test and high voltage is the only way to detect the weakness between them because there's an air gap. And one easy example in life other than motors to think about is like a spark plug in a car. There's an air gap there. It's very small, but it still takes several hundred volts to jump that air gap. It's the same principle for insulation turn-to-turn weakness. There's an air gap there, and in order to expose the weakness, you have to have high voltage. As Swapnil mentioned, very low energy, but you have to have the voltage there in order to jump that gap. Once that fault, if it goes unchecked, and that fault eventually develops into a shorted turn, yes, at that point, any low voltage, inductance or resistance can find it But at that point, it's too late because you only have a few minutes left before that motor will burn to ground because of the tremendous heat that's generated from that fault. So the whole point of the surge test in the high voltage is to find the problem in its infancy months before it gets to the point where it faults together and shorts together in a solid welded short. So you just have to make sure and distinguish the difference between like what fault you're looking at. Is it a weakness or actually like an open or a short? So there are unique differences there.
Thanks, Scott.
Sure.
Our next question I'm going to throw over to Louise. What is the recommended surge voltage for, I'm not mentally geared enough to say this right, synchronous motor and generator exciter rotors?
Okay, so there's no single recommendation. So there are several standards, old standards, new standards. So I cannot say a single recommendation because it depends of many factors. The country, or the company, or the so who is deciding to pick up the right standard? Not the right, the standard that is going to apply for that country, for that customer, or the end user. So I recommend to read the AR100 standard from the EASA organization, EASA organization. You can go to the website from that organization, EASA, EASA, look for the AR100 standard from 2020. So there are, I think, because it is from 2020, those recommendations are updated, taken from many different standards. So you can review, you can download that standard for free. Thanks.
Thanks, Louise. I think I have one more question. I'll throw it over to Scott. Scott, what is the average lifetime of an AC motor? How often is a motor maintenance testing required per your experience?
Most AC motors are designed to last anywhere between 20 and 30 years. So if they're run in an environment that's friendly to them, and we're talking about heat, moisture, contamination, number of starts and stops, those are all factors that degrade the insulation. So if you can do your best, or if the application allows for the nicer environment like that, you will be able to get between 20 and 30 years out of your motor. Part of that is preventive maintenance, and by that I mean like changing out, fan blades, cleaning, lubrication, all those types of typical preventive measures. You'll get a lot of life out of your motor. So if you do have that, what I'll call a regular or kind of a normally applied motor that's not in an extreme environment, for example, typically once a year for testing is all that you would need to be able to identify these problems early enough to be able to be predictive. There are exceptions, obviously. For example, if you might be in a steel mill and you have a very, very hot environment and you have a lot of corrosive elements that can get sucked in from a fan and get ingested into the motor, those are two factors right there that would shorten the life of the motor. So sometimes the suggestion is to maybe test your motor twice a year if you have that option, if you have scheduled outages. If not, you only have annual scheduled outages or sometimes even 18 months. You do the best you can based on your company's policy and schedule. So once a year is kind of a generic recommendation. And then that can be adjusted based on the environment that the motor works in, possibly the age of the motor. If you want to know if it's starting to get really old and you may suspect that it's on its last legs, then maybe test a little bit more frequently just to make sure you catch it and you can do something about it predictively.
Thanks, Scott. I'm going to throw another question over to Louise. How early can you detect turn-to-turn weakness before it falls shortened with a surge test? Is this in terms of weeks, months, or years?
Okay, so one key point of the surge test is you are applying higher voltage comparing to the operating voltage. So if the curve of the insulation between turn to turn is is getting lower, so it will depend of the period of time of your maintenance. I mean, if you are doing the test of the motor every year, so the parameter, I mean the error, pulse to pulse, line to line. So you need to take a look to the graph if you have something that is close to the threshold, to the alarm. For example, our EAR pulse to pulse, you can see a graph with some small peaks below the thresholds. If you have a big peak, but not crossing the threshold, so there is a alarm. What is going on with this insulation? So you don't need to wait 1 year more. If you are doing the in periods of 1 year, the maintenance, you don't have to wait 1 year. Maybe the next, after 3 months, you need to do again the test in order to see the trending of that peak is increasing or no. So there is a good parameter to take a look. Thanks.
Thanks, Luis. Throwing things back over to Swapnil. Swapnil, DC high pot testing versus VLF testing, which is better?
So, Michael, here the question, of course, between AC and DC. So, I'll just give us few factors why DC test is done and in comparison to AC test. So, whenever we see a real life situation or a real life over voltage on a current, it is more of the stress on that motor is more of a DC nature than an AC nature. And so we have to replicate the same issue what the motor faces into day-to-day life. So that's one reason why we use DC. Another reason, if let's say we are using a motor which has insulation already degraded to the bus voltage level, if we use a DC test, the damage done on, of course, there would be an arc and the tester would recognize that. But if we are using an AC test instead of EC instead of a DC, the damage would be much more than what supposed to be with a DC current source. So that's the two main reasons why we use DC instead of VLF.
Right. Thanks, Swapnil. It looks like that's the end of our Q&A session today. I recognize we have a few questions we didn't get to today, but we'll be working to follow up with you offline. If you do have any questions that you didn't ask us here today, but you know you want to talk to us about them later, feel free to reach out to us at any of the contact information here up on the screen, or send us an email at broadcast@megger.com, and we'll be sure to get that to whoever can answer that best. Because much like in the field, for every problem, there's the correct tool. And for every question, there is a Megger engineer ready to help you. So feel free to reach out to us anytime offline, and we will be happy to talk your ear off on any subject you'd like. Moving into a little bit of housekeeping stuff as we head out of here, I do appreciate everyone joining in as always. If you could please take a few minutes to fill out the survey here on the side of our screen, or there on the bottom of your bar, or as we conclude our webinar. We love hearing how you experienced our presentation here and how we can continue to improve upon them. I will also remind everyone that we will be sending out a copy of the presentation, a certificate of attendance, and a link to the video recording of this webinar for about 2 business days. But once again, I'd like to thank you all for attending. As you fill out that survey, you'll notice there's an area to fill out a request for a quote or a demo on any of our Megger products. We'd love to hear from you in that regard. But as we leave, I'd once again like to thank our presentation team and you, the audience, for joining in today. We love having you all here, and we look forward to seeing you at our future events going forward. With that, have a great day, guys. Thanks again.
Thank you.
Thank you.
Bye.
Bye, guys.
Bye, everyone.